All right, so today we're looking at teaching nomenclature tips and strategies. All right, so for those of you who are new, my name is Jeff Anderton. I am the owner and founder of Teaching High School Chem. I grew up just outside Atlanta in the town of Marietta, Georgia. I have a degree in chemical engineering and in secondary science education with a focus on chemistry. And I've been teaching chemistry since 2001. And I am passionate about trying to help you be better chemistry teachers and give you resources so you can have more of a life at home. Because that's what's critical for me. It's been one of those mornings already. We had my 5-year-old just had a meltdown this morning, and then the 1-year-old's being boisterous. And so it's been an active morning. But I wouldn't trade that time for anything else. And that's what I want to try to give y'all is give you tools and resources to make it easier for you to teach, so that you then have more time to spend with family and friends the way you want to spend it outside. So I don't know if you saw this Facebook post I did on the page this week on the Teaching High School Chem page, but it's part of why I think this workshop today is one of the most important, because dealing with nomenclature is critical, because our element symbols and being able to read the symbols on the periodic table is kind of like our alphabet. And then being able to do nomenclature, what we're doing today, being able to do formulas, that's like being able to make words in chemistry. And then when we put that together with reactions and stoichiometry, we start getting sentences and paragraphs, and we start really being able to describe what's going on in chemistry. And if it's not for formulas, if it's not for knowing how to do nomenclature, you can't really tell the story of chemistry. And so that's kind of really why we're focusing on today. So I want to start off with this aspect of what makes nomenclature hard for students, because most likely you come from one of two backgrounds. Either you're like me and you have a chemistry background and nomenclature for you is like really easy. Like I remember during my student teaching, the teacher handed me a sheet of 100 problems. That was a mixture of names and formulas, mixture of ionic and covalent. She said, "How long would it take you to do this?" I'm like, "I don't know." And she's like, "You would be limited by how fast you could write." She's like, "But for students, it's something different." And so we're going to get into that in a second. Or you're someone who struggled a little bit with nomenclature, and you're probably a little bit closer to where the students are. So what makes this hard? So first of all, I'm going to assume you know the basics of nomenclature. I'm not going to go over the basics of why things have certain endings, why certain covalents use prefixes and ionics don't use prefixes. I'm not going to go into the basics of why nomenclature what it is. I'm going to be focusing more on the how to explain it to students. So the first thing about nomenclature, it is higher order thinking. So for somebody like me, and this is what that teacher was getting at, she's like, for you, it's straight memorization. For you, you would be limited by how fast you can write. But think about it. For a student, for them, it's really analyzing at minimum, if not evaluating. Is that they're having to look at a formula. So let's say you got Na3PO4, sodium phosphate. When a student sees that, they have to go, all right, ionic or covalent? That's the first question they have to ask. And then they're like, okay, it's ionic. All right, so what's Na? Na is sodium. All right, is that a normal metal or transition metal? Then they've got to look at the PO4 on the back. Okay, what is that? Oh, that's a polyatomic ion. Which polyatomic ion is it? Oh, it's phosphate. So they're having to answer 5 or 6 questions all in a row in order to get one answer. And so really, this is really high order thinking. You're analyzing and evaluating, and they're really having to work hard. And we have to have that in our mind when we're teaching this, that for our students, they're having to go through a lot of steps in their head before they can get to an answer. And the other thing that just makes this difficult is, there are so many different types of nomenclature, and each type has its own rules. That covalence, everything ends in IDE, but we use prefixes. Then we have metals and nonmetals, no prefixes. Then we add in polyatomic ions, and we got ates and ites and per-ates and hypoites, and we got all sorts of variations here in polyatomic ions. And then we have transition metals with their Roman numerals, which are mostly in the D block, except for the ones that don't have multiple charges or the ones that are in the bottom. And then we got acids, and then we add organic, which I don't even bother covering in general chemistry. I don't cover in organic chemistry in Chem 1. That's it's a whole nother beast that I don't worry about. But there's all these different rules and all these different parts, and that just makes it difficult, to say the least. And so we need to help our students with that. So strategy number one. Strategy number one is to break it into pieces. So what I mean by that is this. If you teach nomenclature all as one big thing, kids are going to be confused. I've tutored a number of kids who had chemistry classes where they did ionic nomenclature, covalent nomenclature, and acid nomenclature in 2.5 weeks total. All taught as one big unit. And, these were kids who weren't the strongest kids and they couldn't keep up. Like I taught them how to do covalent and I taught them how to do binary ionic and kind of gave them a framework a little bit on how to do polyatomic, but I was only seeing them 2-3 times before they had a test on this, and it was just too much information. Because you're going to get things like this. If you just teach it as one big unit, you're going to get kids who think that Na3PO4 should have prefixes. And they're going to, instead of telling you it's sodium phosphate, they're going to say, hey, this is trisodium phosphate tetraoxide. I saw it in my first couple of years of teaching. Every now and then I see it still. Or somebody seeing CO2 and thinking, oh, that's a polyatomic ion. That's carbonite. It doesn't have a charge on it, so it's not an ion, it's a molecule, it's carbon dioxide. But when we teach it all as one big thing, I think kids, they start mixing things up as to what's what. And so it's our job as teachers to break it down and to give them a framework. And as I've said in my other workshops, if you haven't seen those, I believe what I call student-driven pacing. That you don't move on until students have a firm grasp of whatever you're on. Now, not every student, every willing student, every student that's really working hard, that's who I'm kind of gauging by usually. My student who's not trying, they're not going to be my student that I'm gauging my pacing off of. But every student who's willing, every student who's trying, I want them to have a good firm foundation for the most part before I move on. And so, like I said, it goes with student-driven pacing. This is what mine looks like. So I start with covalent, and I start with covalent because it's the easiest. You just have the first nonmetal, the second nonmetal ending in IDE, and you add prefixes. It's really simple. And then by adding Lewis structures, polarity, and Vesper, I just give them more time to practice the covalent nomenclature. As we're doing Lewis structures, as we're doing polarity, as we're doing Vesper, they're getting more and more comfortable with all of that. And I just make them practice the nomenclature as we go along. Like for every Lewis structure, they're going to have to tell me the name. Or if I give them the name, they're going to have to give me the formula. And so I make them practice that as we go along. The second thing I do after that is I do ionics. And then ionic, I break it down. I do binary first, meaning metal and nonmetal. When I say binary, that's what I mean. So doing just a simple metal and a nonmetal. Sodium chloride, magnesium oxide, sodium phosphide, just a metal and a nonmetal. And I do that first, and I make sure they know how to do that. Then I add polyatomic ions, and I make sure they know how to do those. Then I add transition metals, once I make sure they know how to do those. And so I kind of do it that way. Acids, I don't teach at this point in time because we don't use a whole lot of acids in my class. And which ones I do, they just know that HCl is hydrochloric acid. They know that sulfuric acid is H2SO4 because those are usually the two acids I use in class and that they'll use in labs. And so I really just kind of make them memorize those two, and I don't go into all the rules for naming acids until we get to acids and bases in that unit, and then we go over the rules there. Because I just find it's all the rules for covalent and all the rules for ionic is enough for most kids. And so I just want to focus on making sure they have those down because that's going to account for 90% of the things they're going to see. And so I just want to focus on that. And then what I always do is I always finish up at the end of ionic. So like covalent, I do as one whole unit, and I do it as a separate test just on covalent. And then I teach ionic. And then when I get to the end of ionic, what I do is I pull everything together and I start bringing the covalent back in. and I make them identify ionic versus covalent, how to recognize which one's which. And then I give them a flow chart, and we kind of use that as a review. And this is what my flow chart looks like. I've had several different versions with different software that I've used, but essentially it works like this. So I ask them, hey, is the first element a metal or is it ammonium? If it's yes, then you're ionic. If it's no, it's covalent. If it's no, then you rejoice and do your little happy dance, because that means it's easy. Use prefixes, put an IDE on the end. All right, covalents are easy. They like those. If it's yes, then you run into ionics. And this is where I'm talking about. This is major synthesis that your kids are having to do when you ask them to name one of these things or write a formula. Because they got to figure out the positive ion. Is it ammonium or a metal? If it's a metal, is it a representative, like normal S block metal, or is it a transition metal? And even if it is a transition metal, is it one of those exceptions that are in the D block? And then you got the non-metal. You got non-metal or polyatomic ions. And I'll get to what this means in a little bit. I have a pattern that I use to teach my kids how to do polyatomic ions. And that's one of the strategies I'll get to in a moment. And so that's part of it for them. So they have some they have to memorize, but the bulk of the polyatomic ions are going to be this pattern. And so I use these things to help them get going with it. And so this is my flow chart. And so what I'm doing here is I'm giving them a framework that when we do practice in class, when we're reviewing for the ionic test, because the ionic test is going to be all of ionic nomenclature plus throwing in some covalence. And so I'm helping them work through this, like until they kind of get it down. But because I've built all the building blocks, because I didn't move on from this until they knew how to do this, because I made sure they knew how to do this before I added transition metals, because I made sure they knew how to do this before I added these, that they have the pieces there pretty well set, and I'm just pulling it all together at the end. And that's breaking it down. You break it into bite-sized pieces, make sure they know how to do it, and then you move on to the next piece. So that's strategy one. Strategy number two is using the patterns on the periodic table. Most of these are going to come from a woman I did some student teaching. I did half-day student teaching with her. Her name is Veronica Cook. She was at East Paulding High School in Dallas, Georgia, which is another suburb of Atlanta. And she referred to the periodic table as the world's greatest cheat sheet, because it just gives you so much information. Because we can get valence electrons, which will help us do Lewis structures. We can do ionic charges. We can do polyatomic ions. We can figure out some things about transition metals. We can do lots of things with the periodic table. And I always let my kids have a clean, fresh periodic table for every test or every quiz where they need one. And what my kids have learned to do is they know how to mark it up. And this is one of the things I teach them how to do. I teach them how to mark it up. I don't let them bring in their already marked up one. I make them redo it for the test. But like literally, as soon as I hand out the test, it's usually stapled as the last sheet on the test. Most of my kids pull it off and they start writing on it. They write their ionic charges. They write their polyatomic pattern. They do everything they need to do right there. And it works really well. All right. So once again, this gives them, I'm all about giving kids a framework and a structure that helps them learn. But I think that's our job. Our job is to give them the structure, the things to hang their hats on as teachers. And so that's really my big focus. So, all right, let's look at Lewis structures or Lewis dot structures. That's how I learned it. But apparently the correct name is Lewis structures. All right, I was taught kind of a trial and error method. Eventually, once again, I'm kind of a chemistry nerd. And so I saw that there's a pattern that, things in group 17 form one bond, things in group 16 form two bonds, 15, three bonds, and so on. But the patterns don't always work. And so there are some exceptions. And so this is a method I learned from Mrs. Cook, and it uses valence electrons. And the nice thing about it is it always works. And so it's all about counting valence electrons. So first of all, if you're not familiar with valence electrons, which you should be, that outer layer of electrons, S and P, and the way I tell my kids, look at the group number, and it tells you how many valence electrons you have. So group 17, take the 1 off the front, it has 7. These guys, D block, your transition metals technically have two, but the d electrons can come into play affecting that. So when I'm dealing with valence electrons, I don't mess with that. Once again, there are so many complexities and exceptions within chemistry, it's not worth confusing your students over. So there are times where I'm someone who struggles with being technically correct and being too nitpicky sometimes, but I've had to really pull that back when I'm interacting with my students. Because my goal is to give my students the information they need to learn and know what to do. But when I get nitpicky and too technically correct, I give them too much information and it can confuse them. And so I have to pull it back. And that's why I just put a big dash here, because it's like, yeah, you can learn about what happens with the D block and valence electrons later. That's not pertinent to what we're doing, especially when we're talking about Lewis structures, because that's just nonmetals. Okay. So what we're going to do is we're going to count two things and do two subtraction problems. So we're going to count how many we need, and then we're going to count how many we have. Okay, so need is octet rule. Everybody needs 8 valence electrons to be happy, except for hydrogen, which needs 2. And then have is just this number here. And then we'll do subtract to get shared. And this will make more sense when you see an example worked all the way out. All right, so here's what we're doing. We're going to do this. Those are the steps. And we're going to do ammonia as our example, NH3, which looks like this. And so helping students get to this is what I'm trying to do. So first thing I do is I count how many I need. I need 14. Nitrogen needs 8. And then there's 3 hydrogens that each need 2. So that's why it's multiplied by 3, because I've got 3 of them. And then the 2 is because hydrogens need 2. Everybody needs 8 except for hydrogen, and hydrogen needs 2. Then we're going to count how many we have. Nitrogen's in group 15, so it has 5. Hydrogen is in group 1, it has 1. And so we do 5 plus 3 times 1 gives me 8. Then we're going to subtract those. So we need 14, we have 8. And the way I usually explain this to my kids, I've always taught at small schools. And there have been times where we haven't had enough kids to make a full football team. You know, you need, I always get my math mixed up. You need 11 on offense and 11 on defense. So you need 22 players. But what happens if you only have 18 players? You know, and that's what I'll pose to the kids. Like, what do you do? They're like, oh, well, some people play both ways. I'm like, exactly. Some people get shared between the offense and the defense. You know, and usually I'm doing this in the fall during football season, so this makes sense to them. And so that's one of the ways I say it. It's like, all right, so we need 22 players. We only have 18. How many are going to have to play both ways? And they'll think about it, and they're like, 4. I'm like, yeah, 22 minus 18 means 4. We need to share 4. And I'm like, that's exactly what we're doing here. So we need 14. We only have 8, which means we're going to have to share 6 of them. And then I tell them, hey, by the way, divide that by 2, and that gives you how many bonds, because each bond is 2. So this gives you your bonds, the shared number. Then we subtract again. So if I have 8 and 6 of them are being shared, that means 2 of them are left over being unshared. And those are your lone pairs. And so then I teach them, you know, whichever element's written first, unless it's hydrogen, goes in the center, arrange the other ones around it, and start putting your bonds. Key thing with bonds can't go to nowhere. You know, it's amazing to me how I always have a kid want to like draw a bond to here. I'm like, what are you bonding? What are you connecting? There's nothing there. It always makes me laugh. But it's a common mistake. And you just you deal with it and you address it. Or kids want to put a bond between the hydrogens, you know, something like that. And I'm like, no, but they're always going to come from the center and go out, at least early on. And we try to keep it simple. And so this is a fairly simple method that works for just practice of doing these. Because it gives them how many bonds they need, how many unshared they have. It's great for things that are a little more complex, like things that have resonance. This is a great method of just slowing down. I am going through these a little quick, just because I'm trying to get y'all through this in a timely manner. So this is one of those workshops you may want to like rewatch parts of this if a method jumps out to you, or email me and I can maybe send you a handout or something. I've got some of the handouts are going to be on the replay page already. They're already there when we get to the polyatomic ion pattern. That really comes into play. All right, ionic charges. Once again, really simple pattern. The way I explain the octet rule is, once again, trying to think in terms of full valence shells can be confusing to my students sometimes. That sodium, sodium has one valence electron. The idea that it loses that valence electron and now has 8 valence electrons because it has a full shell. My students are like, wait, 1 minus 1 gives me 8? Huh? My students get confused. They don't know what to do with that. And so the way I just generally describe it, I said I kind of changed the way the octet rule is worded just to try to help my kids with it. That they're trying to get to 8 or they're trying to get to 0. Just trying to explain it to them that way. So like calcium's here in group 2. So it can try to get all the way to 8, or it can go to 0. Which one's it want to do? Oh, it wants to go to 0. Exactly. So it's going to lose 2 electrons. And then I give them their charges. I don't know how you write your charges. For me, once again, this is one of those things where my nitpickiness comes in. Charges should be written as the number and then the symbol. If you look on the internet, you'll see it about half this way, half the other way. For me as a chemistry person, +2 is an oxidation number, and 2 plus is a charge. And so I want to distinguish between those two. I don't get into oxidation numbers in Chem 1, but it's something I want to be training kids to be writing them the right way so that when they see oxidation numbers, there's not confusion, okay? Or formal charges if you're doing that with wood structures, which I don't do. Once again, in Chem 1, I don't do formal charges. I think that's more of an AP college topic. And so this is how I do it. So it makes a quick little easy rhyme that it's 1 plus 2 plus 3 plus skip, 3 minus 2 minus 1 minus zip. And so it's a quick little easy little rhyme that works really well for this. Okay, so 1 plus 2 plus 3 plus skip, 3 minus 2 minus 1 minus zip. And it works fairly well just getting those ionic charges, which is helpful. All right, polyatomic ions. This is where we're probably going to be spending a good little bit of time here. So majority of polyatomic ions can be learned by using a simple pattern. It doesn't seem simple at first, but once you get used to it, and once my students hear me say it 100 times from the board, or walking around with them and working with them, they're going to know this pattern. And so I use this for all but 8 of my polyatomic ions. The other 8 they have to memorize, and I'll kind of get to what those are in a second. Because this pattern looks at the nonmetals on the periodic table. And so this is just simply the top right of the periodic table. You should recognize it's kind of the top part of the P block, minus the noble gases. And this is all the ones that are connected with oxygen. All your carbonates and nitrates and phosphates and sulfates all come from this pattern. So that leaves the ones like hydroxide, ammonium, permanganate, chromate, dichromate, peroxide, ammonium, and cyanide. Those are the ones that I make them memorize. So let me run through that again. So, and I think I may have said one twice. So hydroxide, peroxide, ammonium, chromate, dichromate, permanganate, cyanide, and acetate. Acetate's the one I left out the first time. Those are the ones I make them memorize. The rest of the polyatomic ions, all of them come from this pattern. And so I'm going to run through this pattern and try to explain it as we go along. So, all right. So the first thing I do is I give them I've got a handout for this. You can follow along for right now, but on the replay page, so teachinghighschoolchem.com/workshops/replay, you'll see a link to download my handout that goes with this lesson. I used to just give them a blank periodic table, but then I changed how I do it. That I give them something that looks like this with space for them to write in. All right, so these four right here in the middle. So right smack dab in the middle of the P block, above the staircase, is these four. These four all get 4 oxygen. Everybody else is going to get 3. Okay, so that's my oxygen. So now they have the correct number of oxygens. So phosphate has 4, arsenate has 4, selenate, sulfate. I know some of these you don't use. I don't remember if I've ever seen an arsenate compound or a selenate, but it makes for a nice little pretty box. And so the 4 get 4, keeps it simple. Everybody else gets 3. All right. So that's the oxygens. Now the charges. The charges also follow a simple pattern. Group 14 through 17 follow their charges that they would normally have in that group. That phosphide would be 3 minus, so phosphate's 3 minus. Sulfide would be 2 minus, so sulfate is 2 minus. And same, group 17 is 1 minus, so it goes 1, 2, 3 until you get here. And then the way I was taught to do this is nitrate says no, good old NO there, it says no. And then the pattern starts all over again. 1, 2, 3. I had one other student who said, well, what he's saying is he's saying I'm number 1. Number 1, and then it goes back to 1. So you can think of it either way. So the pattern for charges goes 1, 2, 3. Start again with nitrate. 1, 2, 3. And this is all your 8s. So all of them end in ATE. So very simple pattern. The 4 in the box get 4. Everybody else gets 3. And then the pattern for the charges is 1, 2, 3, 1, 2, 3. So I think that's a fairly quick way to now, in literally the 4 in the box get 4, everybody else gets 3. And then the 1, 2, 3, 1, 2, 3 charge pattern in 2 simple rules. I have now just memorized 4, 8, 12 polyatomic ions. And so instead of making my kids memorize all 12 of these, plus all their variations, they just have to learn this, right? Then we get to variations. And so the way I teach this is that there are 4 variations on the standard ATE pattern. So we have 4 variations on chlorate. And I usually slide this in at this point in time. Just, hey guys, if it doesn't have any oxygens on it, remember, that's a nonmetal. And nonmetals end in IDE. Because once again, I'm trying to keep this separate in my kids' heads. I'm trying to give them a structure and a framework. If I don't separate that nonmetal from this polyatomic ions as we're talking about it, they're going to try to blend them back together again. And that just doesn't go well. And so I'm really trying to keep them separate. So I bring it up again. I'm like, hey guys, remember what we just did? It's different. It's not like what we're doing right now. So things that don't have oxygen on them end in IDE. Okay, chloride. Okay, and then what we just learned in that pattern is chlorate. And then I'm like, all right, if it has one more, okay, so how does somebody compare who's hyperactive? Like, oh, they have more energy. I'm like, exactly. So per is short for hyper, and it means it's more. So somebody who's hyperactive is, they're more active. So per means more. So it has one more oxygen attached to it. Charge stays the same. All right. Then one less ends in ITE, chlorite. And then 2 less is hypo. And this is where I tell the kids, hey, you've heard of hypothermia? What's that? Oh, that's when somebody's body temperature gets too low. I'm like, exactly. So when it gets low or too less, we add hypo. And so I'm showing them the hypo and the hyper prefixes and helping them make that connection. But I also tell my kids, it's like, think about it. Look at your book or look at your test. I would say ATE, your 8s, account for probably 95% of your polyatomic ions are going to be the normal standard pattern. Sulfate, carbonate, nitrate, chlorate, bromate, iodate, they're going to be those. You're going to run into, perchlorate's one of the few 8s per-8s that I know of. Then there's nitrite, chlorite, carbonite, but you don't run into a whole bunch of these, and hypochlorite's the only one of these that I've really run into consistently. And so these are fairly rare. These happen a little bit, but it's mostly these. And so I really try to get my kids to focus their energy on learning the pattern and then adjust it. So like when I give them a formula, let's say I gave them CaCO2. And I'd be like, all right, what is that? Well, Ca is calcium. So Ca is calcium, what's CO2? Right, well, it's carbon something. I'm like, all right, what? Right, is it in the box or out of the box? They're like, well, it's outside the box. All right, so how many oxygen should it have? 3. Well, how many does it have? 2. That's 1 less. And so they would know that it ends in ITE. And so I go through this pattern over and over and over again. The 4 in the box get 4. Everybody else gets 3. And then the pattern is 1, 2, 3, 1, 2, 3. And so I do that with them over and over and over again. And then we do variations of it. And so I make sure they get the pattern first, and then I start adding these variations. And then there is one other variation which I don't use very often. You can also add a hydrogen to make it that's the common name, bicarbonate. You also see this called hydrogen carbonate. Big thing is when you add the hydrogen, it actually does change the charge. This goes from 2- down to 1-. But that's one other variation. Sometimes I teach it, sometimes I don't. It just kind of depends what mood I'm in that year. But I really don't use it often at all. All right, so like I said, I've got a summary sheet of this on the replay page so that you can see what I have there. All right, so that's using the periodic table. Now, I want to talk to you about a couple of activities that I use that I find exceptionally helpful. So first one is doing Vesper. Kids really struggle with Vesper. And this is one of those things where it's also one of those lessons where I really don't like the way most chemistry books explain Vesper. Because they use like A, B, X, and it just gets confusing. First and foremost, I don't do exceptions to the octet rule in Chem 1. Because I'm just trying to teach my kids how to do Lewis structures in Vesper. So I don't want to do exceptions to octet rule. I don't want to do the weird things that got 5 and 6 things coming off of them. I just stick with very simple molecules. But the activity I do with them is candy and toothpicks. And so they draw the Lewis structure, and then they're going to stick toothpicks in and other pieces of candy to draw the atoms around it. And what I'm looking for is I want them to see and understand visually the impact that lone pairs have. That if I take something that's trigonal planar, like this, something that has 3 bonds on it, but I add a lone pair at the top, all of a sudden it becomes pyramidal. And I want them to understand that what was planar, this lone pair all pushes these down and away from it. That lone pair is pushing them away. Same thing with a linear to bent, that if I have 2 bonds and there's no lone pairs, then it's linear. But as soon as I add a lone pair in there, or 2 lone pairs, those 2 bonds now become bent because these lone pairs are pushing them away. And I really find that doing this activity where they're putting toothpicks into things and I can come over and I have to check off every single model, it's really hard for big classes, but it really works well. But I walk around and I check all of their models, and so that I can take the model that they have with the candy and I can readjust them and show them, hey, what's going on is this. And then when they see that pattern again later, they know it and they get it right. I prefer the candy versus the plastic models, because the plastic models already have the angles done for them. They don't have to think about it. They don't have to understand it. But with the candy, they're making their own angles. And so it's forcing them to make something look bent or make something look pyramidal in a way that the plastic ball models with the bonds and everything just don't make them do. And kids also enjoy eating the candy when we get done. And so I usually hit this one right around Halloween or right after Halloween. And so I can always get the candy at a lower price, which helps. All right. Then the other one I use, and I've got a link to this on the replay page as well, is my binary ionic activity. And what I do with this one is I use cards to show them that charges have to be equal. And that's what's going on in an ionic bond. And so it looks something like this. So they would have a magnesium card. And the magnesium card has 2 pluses on it, and it's twice the size of the chloride card. Because the chloride one only has a charge of 1 minus. And so here, this is giving them a visual representation of what's going on with the charges. And so they see, oh, wait, I need to add a second chloride in order to make these balance out. So what's your formula? MgCl2. A lot of people teach the crisscross method for doing ionic charges. I do that after I do this, because I wanted them to kind of understand why, because it also solves this problem. You know, kids who learn the crisscross method and only that will try to tell me that this is Mg2O2. And I'm like, no. Their charges cancel each other out. You only need one of each. The one where kids get stuck is when they get to aluminum sulfide in the activity, because they get the aluminum card, they add a sulfide card, and they're like, oh, wait, we're still short of charge. They add the second sulfide charge, and they're like, wait, we're still off. What's wrong? You know, and then they see, oh, wait, we have to add an extra aluminum and an extra sulfide. Now we get this formula. And so it's just a good way for them to see visually and tactilely, you know, for your kinesthetic learners, what's going on. And they can move these cards and arrange these cards. And I've had kids keep these cards for a week, you know, using them to kind of help them do their work and see what's going on. Most kids, by the time we finish the activity, they figured it out and they know how to do it. They can do the crisscross method without having to use the cards. But some of my kids are definitely more visual and really struggle to get this. And this activity really helps them see what's going on, and they can kind of visualize it. You know, there'll be times where like they're working on something. I'm like, all right, think about the cards, you know, and I'll remind them about the cards, and they'll think and they'll kind of figure it out what's going on. All right. So just like I said last week with teaching math, partial credit's your friend, grade this as a skill. Because once again, I'm focusing on the steps, the analysis aspect, especially early on. By the time we get to stoichiometry, a nomenclature question is getting the right formula is 1 point. I'm not going to break it into a lot of different points, because by then they should know how to do this. But when we're learning this, I'm breaking it down. So that kind of, once again, 1 point per step. So for covalence, you know, did they get the right element names in? Did they use the right prefixes? And did it end in IDE? And so for me, that's kind of 3 points. 1 for the right elements, 1 for the right prefixes, and 1 for the right ending. All right, and when we get to ionic, it's a little more complicated. You know, it's like, did they get the positive ion right? If it needed a Roman numeral, that would be another point. Did they get the negative ion right? Did they need parentheses around their polyatomic? Did they get that right? Did they get the charges right? You know, so ionic, depending upon what type we're doing, could be 4 or 5 points each. And once again, because I'm trying to, you know, if I've got a kid, once again, like I've been using sodium phosphate as my example, Na3PO4. If I have a kid who is saying that that's trisodium phosphate, I don't want to mark it completely wrong, because they just put a prefix on the front of it. That's the only thing they did wrong. And so I just want to count that one part wrong, because I'm trying to give them kind of some grace while they're learning how to do this. They're going to make simple mistakes as they confuse things. And by using partial credit, by breaking it up that way, I'm giving them some space to learn. Like I tell my kids with like Roman numerals, because I think one of the hardest things in nomenclature is figuring out what that Roman numeral is supposed to be. If I give you a formula with a transition metal, trying to figure out what that Roman numeral is, especially kids who are weaker in math, that's hard. And so what I tell them is, hey, if you just put parentheses there and just throw in a random Roman numeral, I'll give you half credit for that, because you at least recognize that there was supposed to be a Roman numeral there. Whether you could actually figure out what it was or not is another matter, but you actually recognize that it belonged there. You know, and I'm going to give you some credit for that. Because once again, I want to encourage them to keep trying and pushing. Did they understand that it's supposed to have 4 oxygens instead of 3? Did they get the charge off a little bit and change it? That kind of thing. I'm trying to be generous at first, and then I get a little bit tighter and tighter with my grading as I go along. As I expect their mastery to increase, I'm counting fewer and fewer things. So that by the time we get to the final test, to me, most ionic things are 2 points. Did you get the positive ion right? Did you get the negative ion right? And that's it. And so it just gets a little more strict as I go along. All right. So I've gone over this. I've been thinking about it just as I've been emailing back and forth with a couple of people over the last week. Once again, if you've got any comments, any questions, emailing me is a great thing to do during the week. I'll respond as quickly as I can. It is summer with the kids home and everything. But when you're growing in content, if you're in that stage where you're trying to learn the chemistry content, you are that's a hard place to be as a teacher. Even in which you're trying to learn all this over the summer, because there's just so much stuff. I honestly think out of all the high school sciences, chemistry is probably the hardest. It's the most abstract. Physics, you can kind of relate to. It's kind of real world life, but the content in chemistry is rough and it's hard. And like I've mentioned, that's why I created my crash course, to kind of give you one place where, kind of like how I've been trying to teach y'all some things, that's where I'm teaching the content in the same way that I'm teaching this, and really trying to teach it in a way, and it's one place. And you're hearing it all in one consistent way, because if you're trying to teach yourself across all the different things on the internet, and you're trying to read your textbook, which most likely is written by somebody with a PhD in chemistry who can't really explain it to somebody who doesn't understand chemistry, because I've really found most chemistry books require a chemistry degree just to understand them. They're not good resources for a young teacher trying to learn the content. They're not a good resource for your students to read. And so that's why I'm doing my crash course. That's why I'm offering that. And then growing the communication. If you liked what we've been doing here, trying to figure out how to teach it and how to communicate to your students, that's the other thing I really want to do. Because like I said at the beginning, my passion with teaching high school chem is to help you. That is my passion. My passion with teaching high school chem is to help you be the best possible chemistry teacher you can be. If you're still growing in content, I want to make you the best, most competent, prepared, and confident teacher you can be in terms of the content before you walk in that door for your classroom. If you're in the stage where you're trying to grow in communication, I want to help you there to grow in your ability to help all of those students, not just your best and brightest, know it and learn it, but to really help every willing student get this and be able to do well in your class. Now, once again, well depends. For some kids, that's a B. Some kids, that's an A. I've had some kids where it was a C. And I was more excited about that C than I've been for a lot of kids' A's, because that kid busted their butt and that's what they could do. But whatever success means for those kids, I want to help you be able to explain it and communicate it to them and help them succeed. But then taking it another level, for both the content and the communication, my passion is to give you back time. That's why I started this, because I wanted more time with my family. I love my kids, I love my wife, and I want to spend more time with them. I want to spend time like we did doing, walks yesterday, going for a walk in the rain. It was fun. So like I said, the crash course is everything you need presented with one voice, and it's consistent, and it's a way that you can understand so that you can be confident and then be able to turn around and explain it to your kids. Because I think there's a few things worse than walking into a lesson knowing that you really only have about a 75% grasp of what you're about to teach. It makes me feel icky just even thinking about walking into a classroom like that. And so I want to create Crash Course to help with that problem. Okay. And then, like I said, I've got my academy, which is my monthly membership. Once again, giving you everything. And this one is the big thing here is that it's every resource you need. It's all the classwork assignments, all the homework assignments, all the quizzes, all the tests, all the review sheets, labs. I'm constantly adding to it. I'm adding teaching PowerPoints this summer for every unit. I'm adding new videos. I'm updating my videos this year. It's going to be kind of my project throughout the year. I'll be staying ahead of where you are, hopefully, throughout the year. And I'm adding new labs this year. That's my big focus this year. So those are kind of big things I'm adding as we go along. And so you can, once again, I've mentioned this before, there's a sample for the membership. If you looked at it before, you can look at it again. This one's updated. I've changed kind of how I'm changing it. I've got the videos so that they play on the page instead of having to be downloaded. And I've got some other features going on there. All right. I'm going to be doing early bird specials this week. So if you go ahead and register for the crash course or the academy membership, that you're going to get an early bird bonus. And I'm going to offer this again in July, but it's going to be a much smaller bonus. So right now, for either of those, I'm going to close the academy membership in probably end of August, beginning of September, right around there, right around Labor Day. And crash course remains open all year, but if you enroll this week, you get an early bird bonus of 20% off. And so the crash course drops down to $237, or 3 monthly payments of $87. And then the academy drops down to $37 a month. And because I want you to have time to look at these resources over the summer. And once again, be prepared to walk into your classroom in August or September and be prepared for those kids. And so I want to offer this early bird bonus to just make it more accessible to you, and just to give you that opportunity to hop in there now and just be confident and prepared and just have that sense. Because when you're having to teach yourself and prepare as you go through the year, it saps you. It saps you in the school, in the classroom, and it saps you at home. And that's not what I want for you. I want to give you every resource and every help I can to really, once again, excel in the classroom, because when we're doing well in the classroom, it gives us energy to take home. Because when we're struggling in the classroom, it saps energy out of us, and then we have less energy to take back home to our family and friends. I know when I'm exhausted, I don't make a very good husband. When I'm at wit's end, I don't make a very good father. I make an okay one, but it gets hard. And so I want to equip you with those things as well. And so that's what my crash course is for. If you're working on the content side of things, that's what the academy membership's for. If you're working on the communication side of things. And I just want to be there to serve y'all. So if you have any questions about either about the crash course or the academy membership, or if you have any questions about kind of what we talked today about nomenclature, you can ask me those things. The handouts and the activity for the ionic nomenclature is all on the replay page, teachinghighschoolchem.com/workshops/replay. And if you're interested in signing up for the crash course of the academy, which would be an important thing to say, just go to teachinghighschoolchem.com. You'll scroll down, you'll see where to click to go to either of those. And so if you're interested in doing both, then just email me and we can work something out price-wise to make that work for you. And so hope y'all have a great rest of your week, enjoying your summer. And once again, if you have any questions, I'll be on for the next 5-10 minutes or so. And so thank you.